Hey friends, let's have a look at problem 1110, delete nodes and return forest. This is actually a very interesting problem. So in this video, we're going to use this problem to understand recursion. Here we are given the root of a binary tree, and each node in the tree has a distinct value. So this is very important. The values are distinct, so that you can make a one-one correspondence between the node and the corresponding value, right? So after deleting the all nodes with a value in this list, so we are left with a forest, so which is a disjoint union of trees. So we want to return the roots of the trees in the remaining forest, and we may return the result in any order. So here are two examples, right? In the first example, we notice that we need to delete node 5 and node 3. So notice that node 5 is a leaf, right? If you delete that, so it just does not change. We don't need to return this 5, and because there's no children. And for the node 3, so actually if you delete this 3, so you need to reset the red subtree of the node 1 to be none. And also this deletion produces two trees or two forests are rooted at 6 and 7, right? In other words, the output will be a tree rooted at 1 and a tree rooted at 6 and another tree rooted at 7. So this is the first example. Actually, from this example, you can basically digest the main points for this problem. The second one, so we are going to delete 3, right? So the 3 is a right child of the node 2, right? So similar like here, right? The constraints for this problem are actually mainly the problem size, so which is not very large, so that we can pay less attention on this. But it's still good to analyze the time complexity of the solution if you dig deeper, right? So this is actually a good problem for practicing recursion. So here I'm going to write something so that we can make as principles. So recursion, basically there are 3 ingredients. So one is base case, right? So you can have some base case, you get the solution. And the second is reduction to the base case or base cases even, right? So the third ingredient is self-call, right? If you write a recursion function, you need to call itself in the function body. So this is the general recursion. And for this problem, some main points. There are 2 things. First, we need to distinguish between leaf node and non-leaf node, right? So this is the one thing. Another thing is we need to properly reset the left and right subtrees for a given node. For example, here, if 3 is deleted, we need to reset the right subtree of 1, right? So these are the 2 main points. So next, we're going to first write the solution, and then we want to explain the delicate part of the solution. First, notice that we want to check, for example, if we traverse this tree, we need to check with the value. If the value is inside this list, because list is not very fast for membership check, we're going to convert this one to be a set. So we can do this. So to delete, in order to distinguish with original variable, I'm going to use to delete set. So this is just change this one to a set. So this is a type conversion. And then I'm going to write a hyperfunction. So you can understand this hyperfunction as a worker, right, to modify this result list. Because this result list is mutable, we don't need to use the keyword non-local or global, right? So here define the hyperfunction. So this function accepts two arguments. One is the node, or I write like root. Another is if it's a root. So you given the node and let's check if it's a root. So then we can try to write this function. First, let's look at the base case. So if not root. So in this case, we have a null tree. So we largely use this case as a stop condition. So we're going to return none, right? Let's see. This is one case. And then we're going to check if this root is going to be deleted or not. In other words, we want to check if its root value is in this toDelete set, right? So let's do this one, root deleted. So this is a Boolean variable. So it's basically check if root value is in this toDelete set, right? Then the thing is that if it's root, if it's a root, in other words, it's a root of a potential tree, right? Though and not root deleted, right? So in other words, this is the root. This root is not deleted for sure. This root should appear in the final result. So we're going to do result append this root. So this can be regarded as another base case, right? So now we want to write the recursive call. So here, let me first write this root left. So we are going to use this assign. So we are going to do root left. But here we want the second variable to be root deleted. And similarly for root right, I'm going to write like this: root right and root deleted. Let me first finish this overall function, and then we are going to digest this part, right? So then for this function, we are going to return something. We are going to return null if root deleted. So in other words, if this root is to be deleted, then this root will not appear in the final result. Otherwise, else we just return the root itself. So notice that here the root we returned is already modified by this two line of codes, right? As we mentioned, for example, if we delete 3, so we need to modify the right subtree of this one. So this is the overall function. Let me first make a function call, right? So hyper root. So we want to check. So here originally it's for sure it's the root, and then we are going to return the result. So this function returns something, you can write like this, or you can write like using the dummy variable. So let me first check the correctness of this code and then explain this hyperfunction. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the cases. So now we are in a position to explain these two lines of code. The first question is why do we write root deleted in the two lines below, right? So this is the first question we need to answer in order to have correctly understand this overall hyperfunction. So you can understand like this. So if root is deleted, or in other words, if this is true, then the root left and the root right can produce new roots, right? So that's the logic. So let me comment here. So if root deleted is false, let's use other side, right? Then because we didn't delete this root, right? Then root left and root right can never appear in the final result, right? Because if the root left and the root right are not to be deleted, and then they should be as the children of the root originally, right? Because we are going to put the root in the final result. Then this sentence is correct, or this pointer is correct. Or put it in another way. So let's write more so that you can better understand. If root deleted, it's true. So in this case, root left and root right can potentially yield new roots for the resulted forest, right? So that's why we have this this call of the function like root deleted. So we write here root deleted. And another thing is the second question is the assign. How to understand or digest the two assign symbol below. So this is also important because, as we mentioned, so we need to properly reset the left and right subtrees. So you can understand like this. So if root left or root right is to be deleted, right? Then according to this recursive function, if root is to be deleted, we are going to return null, right? For example, if this root left, so for example, let's use root right, like use here 3, right? So 3 is to be deleted. And then this function, if you call this tree rooted and 3, it's going to return you none, right? Then this corresponds to set when the right subtree is null. This is the line of code. Similarly, if the root left to be deleted, right? So we are not going to return anything. We are going to return null. Then this corresponding to set root left to be null. In other words, so these two lines of code, or each line of the code, actually did two things. First, we are going to do this recursive call. In other words, we return null or the root itself, but the root is the tree for the root for the tree corresponding to root left is modified. So this is one thing. Another thing is that we properly modified or reset the children for the root. That's the role of this two line, right? So when you understand this, so you can understand, oh, for this function, if root overall, if root is to be deleted, anyway, we are going to return null, and then we don't need to modify that. If the root is not to be deleted, we need to modify this part, right? Then in the process, we actually already also modified the result variable. So this result variable, because this function is a recursive call, this result, after you call this function, it will be collecting all the possible roots of the forest. That's why we have this one, and then we return this result. So basically, that's an explanation for this daily challenge problem. So if you are interested in more such analysis, you can check out our YouTube channel. With that said, I guess that's it for the current video.